Yeah, let's begin. So today we are going to talk about the surface integral. Vector fields. First, let's recall what we did in 1D. So in 1D, we consider the line integral or vector fields f, and so we denote it by f dot d gamma dr, and graphically, probably you have a curve C, and in the background ambient space, probably 1D or 2D, you have vector fields F. In particular, you have the vector fields along the whole curve C. Okay, and then the definition or the way to compute the line integral of second kind is by parametrization. So as what we did last time, so a b f dot gamma prime t dt. If we would like, we can rewrite this as a b and f dot t. I'll explain what is t and the ds. So here, tangent t is a unit tangent vector of curve C. And then here ds just usual arc length. Or if you like, you can probably better write down in this way. Then it's independent of coordinates. C f dot t ds. Okay, so if you look at this part and this part, and then you noted that what we did is transform the line integral or vector fields to a line integral or a function. So how we did that? We introduced a geometrical quantity, geometrical vector fields, so that you can do dot product. After dot product, your original data, capital F, is transformed into a scalar function. So in 1D, the actual geometric quantity is unit tangent vector field associated with your curve C. Okay, now in 2D, we will carry out the conjunction similarly. But first, let's very roughly introduce a notation. So here you have capital S and over arrow, and so this indicates we are considering a surface integral or a vector field. Okay, we don't know how to compute it, but first, what is the definition? Neither, but physically we can introduce the idea first. Suppose you have plane. By rotated, you can assume it's xy plane. And in the whole space, you do have, as before, you do have vector fields. Of course, here we consider in 3D. Okay, then if you restrict to some domain in xy plane, so probably this one, then you might be interested in the following questions. What is question. What is the rate of flow through, so let's call this S, through S. Okay, so if you look at that, I will probably so actually when Faraday introduced the idea of the fields, he viewed it as some lines, force lines passing through S. For example, actually here we are counting how many green lines passing through S. Okay, but how many should be quantified not as how many numbers, but as just some integrals. We will not get into the detail of the physical explanation, but it's a good idea to have some picture inside. So we are counting the green lines passing through the blue region. Okay, and there's one crucial point need our attention. That is the following fact. So only velocity in z direction contributes in the above situation or scenario. This is because this is easy to understand physically. So suppose you have this region and your field is parallel to the xy plane. Then there's no green line passing through the region, except infinitesimally one, probably just because it's on the plane. But since it's too thin, we can omit that. Okay, so this no contribution. So that indicates, although our vector field, so remark, although our vector field F can be arbitrary, but the contribution comes from the z direction in the above case. So what is z direction? Z direction just z direction is the normal direction of xy plane. Okay, therefore, if you write down your vector field F in components as F1, F2, F3, then finally you should integrate. So in the above case, let's compute F dot ds. So that's what we need to define. But from physics, it should be integration over S, only the z component contribute dA. Okay, should be, so here should be. It's but this form is still coordinate dependent, because if you choose your plane to be YZ coordinate, YZ plane, then you need to choose the X component. Okay, then we need to, I will not write down the other cases, even you can have some screw planes in 3D or curved planes, but then we have another way, which is coordinate free, to write down the above observation. That is, coordinate free interpretation. We need to integrate f dot normal direction of the surface. Okay, then very roughly, but this is true, we can define the integral of vector fields along some surface to the surface integral of the dot product between vector field f and the normal direction n, and then do the surface integral of functions. Now this is a scalar function. Okay, if you recall what we did in 1D, you noted that here we insert another geometric data, the unit tangent vector, so that you can do dot product and transform the surface into the line integral or the vector field into a line integral or scalar function. And for surface, we did the same thing, right? We insert the geometrical data associated with the surface. This n depends on how your surface curved in 3D space. What's the position of your S? And okay, so this is a normal direction. Of the surface at each point, right? It's changing from point to point. You have different normal direction. So this actually is the normal direction of the tangent. Tangent space, tangent plane of the surface at each point. Okay, this is quite satisfying answer, and we're almost done because we transformed the original problem to the one we already know how to solve it. But here we have a question. Immediately we have two questions actually. So if you look at the picture carefully, then you notice that, so if you look at this one, you notice that the numerical quantity of the integral depends on the choice of the normal vector. The choice of the normal vector matters. So for example, if you choose your normal vector to be this one, then the integral, then you do dot product, what do you have? So this will be positive, right? Because the yellow one and the green one in the same direction. So this will be integral of some positive function. Positive function ds in our case. But if you choose the opposite direction as your normal vector, then what do you have? You can still use the formula because we didn't see which direction you should choose, right? ds equals integral over s, and then you see you have negative function inside. Okay, then the problem is they cannot be equal. But on the left-hand side, you do have, they all present the original surface integral before introducing the extra geometric quantity, the normal direction. So they are the same. They should be the same. So this is the first problem, the definition. Lacks something. Something are missing. Something is missing. Okay, then question 2. So for the plane, you can always choose a normal vector, either this one or that one. But then the problem is, for a curved surface, you might have trouble to introduce some continuously changing normal direction. So, for example, we cannot introduce continuously changing normal vector for certain surfaces. So if you search on, I will not discuss in detail these exotic cases because we will not do surface integral of vector field on those surfaces. But you can search on Wikipedia or Google, find the following example called Mobius strip. So basically you have, so suppose you have a strip. You have strip, and if you glue these two sides together such that the arrow in the same direction, then you have, for this case, what you have is a cylinder, the surface, the sides of the cylinder, right? Now, if you do an alternative way for the gluing, you go this way. You glue these two sides together, but still make sure the arrow are in the same direction. Then what do you have? You will have this one. So you will have go this way, and then suddenly change to the bottom. And then the bottom go this way. So they go up. Up. Yeah, you're still up. Okay, then you can prove it's not easy. You can prove we cannot do we cannot find the continuous changing normal vector for this surface because the reason is following. So suppose you choose normal vector here and then you change it with the point. Then you have this one, this one, this one. But then when you flip it at this point, then when you cross it, your normal vector becomes this one. So when you turn back, they have some gap here, right? When they close enough, the direction is opposite to each other. So you cannot do that. Okay, so this is a second question. We cannot do the normal direction globally. So to solve these two questions, we need to introduce the following idea, what is called orientation. And so the definition is like the following. If it is possible to choose a unit, the unit is not that important because you can always normalize it at each point x, y, z on the surface S, so that n varies. N is a normal vector continuously over whole surface S. Then S is called oriented surface, and the given choice N provides S with an orientation. And immediately we have the following remark. So there are two orientations for any orientable or oriented surface. Okay, so probably I should change this to orientable. You just flip it, right? You have, suppose you have one orientation, then you flip the normal direction to the opposite one. Then globally, you also flip the one. So I just think about this example. Suppose you have surface like this one, and then you have the orientation. So the normal vector you choose just point outwards, and then suppose suddenly they flip it together. Point inwards. Okay, then you have two orientations. And this is a very hard problem to decide which surface has orientation, which are not, and it's not a purpose of our course. In the following, we will introduce some well-known examples of surfaces with orientation and give you the way to construct the orientation or pick out the orientation easily based on the equation or the data. So choose nature orientation. First example, suppose we have graph x, y, g, x, y. Then no matter what g is, we can always define the normal direction globally to be the following data. So outside you have normal factor. It's just a constant because you want the normal vector to be unit normal vector, unit. So you normalize it by some quantity. And the inside you have x partial, yeah, I'll take this, gx minus gy and 1. And this is what we done before, that we verified that this vector is tangent to the tangent plane at each point for the surface S. Okay, so this is one direction, and of course you can take a negative n. Negative n, you can define to be negative 1 over blah blah blah, and then inside just the same thing. And I would like to compute one more step. So no matter what it is, outside 1 over square root blah blah, it's a positive number. Inside gx, gy, I don't care about these numbers, but I do care the last number. So an easy way to distinguish these two orientation is to look at the last component. So notice that this orientation, I mean the n, has positive z component. So in other words, what does that mean? So suppose you have graph and then we always choose the orientation upwards. Therefore, we call this the upward orientation. The graph. For graph, you can always do that, but you can think about this. In general, you cannot do that because you cannot make sure the last component is always positive or negative. Okay, next example is suppose S is parameterized by a domain R in 2D. So suppose you have this one. No matter what the domain is, you have parameterized gamma, no matter what gamma is, I don't care. And then here you have some green part. This is your S. Okay, as soon as you can parameterize it by some domain 2D, then you have a natural orientation associated with that. So let this be U and V, and define the normal direction to be gamma U cross gamma V divided by gamma U cross gamma V and take the norm. So what's the geometric meaning? So suppose here you have two directions. So one is delta U, one is delta V, and then on this side you might have the gamma U dot delta U approximately gamma V dot delta v. And then you choose the normal direction, just obey the right-hand rule. You just choose to be this one. Okay, since u and v are defined for each point in S, so this normal direction can be chosen just by this formula. Okay, so that means as soon as you have parameterization in 2D, then you are done. You can choose this. But here, this is not as canonical as a graph case, because definitely you can change your orientation. Change your parameterization, and then that will give you a different orientation possibly. Okay, so this is just one of the choice. So we don't have specific name for this orientation. Okay, next case, suppose S is a closed surface in 3D. So that means there's no boundary. You do have a lot of examples of that. For example, you can single some deformation of surface of the sphere. You just squeeze it, and then you have this type. And or you might have some donuts, or you have some donuts with 2 holes. You just eat one. Okay, then what do you have? So all these surfaces are examples of closed surfaces, and for closed surfaces we can do the orientation canonically. So how do we do that? Choose the unit normal vector pointing outward. So because in all these cases, you separate the whole space into 2 parts, inside one which is bounded, outside one which towards infinity. So you can always choose the direction points outwards, for example. Of course, you can choose inwards, but then you have another orientation. As we said before, as soon as you know one orientation, the other one is easy. Okay, so in this textbook, we call the outward one the positive orientation. Call it positive orientation. And then for the inward one, we call it negative orientation. But probably this notation not that canonical. In different textbook, they might have different name for that. Therefore, the geometrical meaning probably is more important. Okay, now we turn back to the original definition. We can do a very rigorous definition now. So suppose S is equipped with an orientation n, which is a unit normal vector. Okay, then we can define, the surface integral of the vector field f by the following surface integral of a scalar function. Everything is same as before, but here we make sure our orientation n, or the unit normal vector field, is well defined and cause no trouble. So inside you still have the dot product between f and n. And sometimes we also call this, give this a physical name. This integral is also called the flux, or f, across surface S. Okay, next we are going to carry out some computation for different cases. And so first, suppose S is parameterized by gamma UV, and UV is in the region R. And as before, we can take the orientation to be gamma U cross gamma V dot gamma U cross gamma V take the norm. Okay, I will first stay and I will make a very important remark. And then suppose you choose this orientation, then the surface integral f dot ds can be computed by gamma u cross gamma v divided by gamma u cross gamma v and ds. Okay, and now let's recall the fact we learned before. So here for surface integral of a function, we pull back to the parameterized domain R. So, and no matter what it is, inside is a scalar function. And then outside, remember last time we did the computation, so it should be given by a norm of gamma u cross gamma v dA. So here R, so let me draw a picture again. R is like this, and surface S is probably given by this one. Okay, now you can cancel out the length part, the norm part, and then you derive the following formula. dA for the parameterized surfaces. Okay, and before we give an example, I would like to make a remark. For problems on surface integrals of a vector field, you should be given an orientation a priori. Either direct or implicit. Directly or implicitly. So if you do some calculation, I suggest you either, if the problem give you an orientation, then you take it. If they don't, you state clear which orientation you are considering. Okay, because if you flip the orientation, you have a different answer, different by a sign. So that's a lot difference. So make it clear which orientation you are talking about. Although for some problems, it's really a convention that, for example, you always take partial orientation for closer surface, but not always. So I would suggest you to state clear, if you could. Okay, now let's look at one example. So find the flux of the vector field f x y z equals z y x across the unit sphere x squared plus y squared plus z squared equals 1. So for example, this problem, they didn't give you the orientation, so I would choose 1. So by convention, I would just choose a partial orientation, choose a partial orientation. Okay, then this actually a little bit tricky, but I leave it to you, because here you have two ways to define the orientation. Think about first one is view it as a closed surface, so you choose the outward one. Secondly, you view it as parametrized surface, then you choose gamma u cross gamma v divided by gamma u cross gamma v norm. But of course here the choice depends on your parameter uv. Okay. But as soon as you choose this one, then you should obey it. This is clear. This orientation is clear. What does that mean? So no matter what orientation you choose, if it in the different orientation, you need to flip it. Okay, and here we parameterize the surface by spherical coordinates with radius variable equals 1. So parameterization is given by sine, phi, cosine, theta, sine, phi, sine, theta, cosine, phi. Okay, and of course your phi is between 0 and pi, theta is between 0 and 2 pi. And then first let's compute the cross product. So this actually we computed it before, so I will just write down the answer. Sine phi square cosine theta, sine phi square sine theta, sine phi cosine phi. And I will make a remark. This point outwards. Why? So please verify this. Probably we don't know this point outwards, right? But after computation, you can show that this actually point outwards. Okay, and then you normalize it. Actually, to apply the formula here, you don't need to normalize it. You see? Okay, so next we will compute the dot product. But first, let's substitute the parameterization into your vector field F, capital F. So because your capital F is z, y, x, so now you have cosine phi, sine phi, sine theta, sine phi, cosine theta. And then you do dot product. you do have sine phi, cosine phi, cosine theta, plus sine phi cube, sine square, and plus sine phi square, cosine phi, cosine theta. Let's see if we are in good shape. Yes. Okay, then we can do the integral. By the formula, we transform that to a double integral from 2 pi, from 0 to pi, and inside you have 2 sine square cosine, 2 sine square phi, cosine theta, plus sine cube phi, sine theta square, and d phi, d theta. Okay, then, oh sorry, here you have, this is theta. Okay, then we can compute it. I will split these two parts, and because of the time, I leave it to you to, sorry, this is from pi. Sine phi d phi times 0 to pi cosine theta d theta. This is the integral of the first item. You just split phi part and theta part. And then plus, do the same thing from 0 to pi sine cube phi d phi times from 0 to 2 pi sine square theta d theta. So this is the second part. You also do the splitting, and then you can calculate those integrals in one variables carefully. So I will omit the details. You do have 4 pi over 3. Okay, next, let's exhibit one example of a graph. So suppose S is a graph fxy, then we can further simplify this quantity, this function. So suppose f is given by f1, f2, f3, or pqr in the notation we used for the green theorem, pqr, and dot minus gx minus gy1. So this will be minus p times gx minus q times gy plus r. You need to compute this guy. Okay, I don't suggest you to remember this formula. I'm just telling you for the graph case, you have easier computation. So evaluate the surface integral where the vector field is given by y, x, z, and S is the boundary of the solid region, E enclosed by the paraboloid z equals 1 minus x squared minus y squared, and the plane z equals 0. So solution. Okay, I would like to first draw the picture. So actually you have two parts. This is one part, and also you have something something in the bottom. Okay, so let me call this as S1, sorry, S1, and then the bottom as S2. Okay, and now, first let's decide the region S2. So we do intersection. Z equals 0, so this is x, this is y, this is z, and z equals 1 minus x squared minus y squared. So you have the following formula. Okay, so S2 is given by the unit disk in xy plane. Okay, and then we can compute the. Let's first parameterize both surfaces, and then we give orientation, then we do calculation. So, because the orientation should be given globally, so if you decide the orientation for S2, you cannot choose the orientation for S1 freely. So we'd better first decide the orientation and then just narrow down to small portions of the whole surface. Okay, so for S1, we do have the parameterization because it's a graph now, so you can choose the parameterization x, y, 1 minus x minus y squared, and then xy is in xy in unit disk. So I would like to draw a picture. So on this side, you also have x and y. But this is just a parameterized space. Sorry. Parameterized space. Okay. So parameterize. And here the equation is x squared plus y squared less than or equal to 1. Okay, next we choose orientation outwards as usual. Choose a positive orientation. And then for the green one, so the orientation is downwards. And then for S1, the orientation is go outwards. Okay, so we first calculate the surface integral over what's S2 f dot ds. Here you have orientation, particle orientation. Then by formula, it just S2 and f dot, because the orientation is negative, so let's write down it carefully. So in xyz coordinates, it's because y is, f is y, x, z, and then the orientation is 0, 0, negative 1. Okay, so this is a dot product. Then outside you have ds. And simplified, you have negative z ds, but because we are considering on the surface S2, so z coordinates is 0. Therefore, you don't need to calculate. So this is step 1. Calculate S2. This is pretty easy. And then step 2, let's calculate the integral on S1. So S1 f dot ds is given by f is y x z dot, and here we have the unit normal vector is given by, sorry, not unit normal vector, just we need to compute a little bit, but I will omit that here. Gamma x cross gamma y. So we already computed before. This is negative gx negative gy plus 1. And since your function g is 1 minus x squared minus 2y, so this is 2x, 2y, 1. So I make g is 1 minus x squared minus y squared. Just like here. Okay, so here you have 2x, 2y, 1 dot product. Okay, and then you have dA. Oh, sorry, here you should be, let's call this as R. The integral should be on R. Okay, now let's compute it. So simplify the inside. You have 2xy plus, oh, sorry. Here z, you need to substitute 1 minus x squared. We can do it at this step. 2xy plus 2xy plus z dA. But here z, you need to replace it by your parameter. 2xy plus 2xy plus 1 minus x minus y, x squared minus y squared dA. And then what do you have? You have 4xy plus 1 minus x squared minus y squared dA. And region R. Okay, since region R is a unit disk, we use a polar coordinate, and therefore you have 0 to 1, 0 to 2 pi, inside 4r squared cosine theta sine theta plus 1 minus r squared r dr d theta. This is by the formula for polar coordinates. You have extra r here. Okay, next we can first do the theta integral, and then you have 4r squared, and here you have sine square theta, and plus divided by 2, and plus 1 minus r squared. Oh, sorry. Yeah, you can do like this. You have extra r here, so I will better right here r and theta. 2 pi 0. Outside you have integral with respect to r, and it's easy to see this part is gone because the endpoint is 2 pi and 0. Plug in, you have 0. And then for the second part, you can evaluate. You have 2 pi times r minus r cubed, integration from 0 to 1. Okay, then you have 2 pi r squared divided by 2 minus r cubed divided by 4, evaluate at 1 and 0. Therefore, you have 2 pi times 1/4, which is pi over 2. Okay, although the last step is trivial, but I would like to write carefully, because ideally you need to sum up the two small integrals plus f dot s ds s1. So you have 0 plus pi over 2, which is pi over 2. Of course, here the orientation is positive. As I mentioned before, you need to be very careful about the orientation, and it's better to state at some point what is your choice of the orientation. Okay, I will stop here.